Now the preparation of alkyl halides with thionyl chloride in the presence of pyridine. So this process is famously known as Darjan's process. Okay. The overall reaction can be given as this. Alcohol with, so this is thionyl chloride. SO2Cl2 is sulfuryl chloride, but this one, SOCl2. This is thionyl chloride. Yeah, this of course can be written as, for convenience, let us do it this way. We get alkyl chloride, HCl, and the thing that is remaining is SO2. RCl plus SO2 plus HCl, right? You know, this process is in fact advantageous. For the preparation of alkyl halides from alcohol. But why? It is because, you know, these byproducts, sulfur dioxide and HCl, are gases. So they can be easily removed from the mixture to get the alkyl halide easily. Okay. Now let us see the mechanism. This is thionyl chloride. Okay. Chloride is last. And we'll get R O H H double bond O Cl. Now this Cl minus abstracts the proton. We get RO, then S double bond O Cl. Okay. Then with pyridine. Now pyridine comes into picture. Now this lone pair attacks and the chloride goes off. See, we get RO S double bond O, then the pyridinium part, nitrogen with a positive charge. Okay. Now this chloride attacks the alkyl group from the backside, as I said, even earlier also. This is SN2 with inversion due to backside attack. Now, as and when the chloride attacks, this comes here and this goes towards the positive charge. So that is how you get the final products. RCl, SO2, of course, the pyridine. So whenever pyridine is used along with thionyl chloride, see the mechanism is SN2. Okay. But in the absence, it is going to be SNI. We'll see that. Now, in the absence of peroxide, the mechanism will be little different. Now, chloride is last. We get this. This will give us ROSOCl. Now, from this, the mechanism will be different. See, this chloride attacks the alkyl group from the same side of it. Let us say from the front side. And say this all is happening within the molecule. So this, of course, is known as SNI, where this I stands for internal. The attack here is the same side attack. Now the same side attack gives us a retention product. Okay. Finally, we get RCl, I mean alkyl chloride and sulfur dioxide. Anyway, here we got HCl. Along with this, you can write HCl. So this is very interesting where just because there is no pyridine, the mechanism is quite different. SNI, in the presence of peroxide, in the presence of it's pyridine, in the presence of pyridine, it is SN2, but in the absence of pyridine, it is SNI. Okay. Now, one more. Using HX. See, with HX, the reaction takes place in the presence of anhydrous. See, it can be given as HX with, of course, anhydrous zinc chloride. This, in fact, can be taken with HCl and the anhydrous zinc chloride. We'll see this first. Here you get RCl and then water. Okay. You know this mixture HCl and anhydrous zinc chloride in 1:1 ratio is known as Lucas reagent. A very important reagent used for the distinction of primary, secondary, and tertiary alcohols. Okay. Name of this method is Grove's process. Again, a very important one. Now, here in place of this anhydrous zinc chloride, which is in fact acting as a dehydrating agent, we can use concentrated sulfuric acid, pyridine, or even this dimethyl amine can be used. Okay. These are all dehydrating agents. Remove water. Let us see the mechanism. We know that ZnCl2 is a Lewis acid. Okay. With the alcohol, this of course is a Lewis base. Electron pair donor. Now, We get ROH, a pair of electron. Then, of course, this is ZnCl2. Excess of electron is present at zinc, so minus charge. Okay. Now the chloride ion from HCl. Attacks. This alkyl carbocation. You know, here, this is the intermediate, R plus. We get the alkyl chloride. And look at this. ZnCl2. So this can, of course, be given as ZnOHCl2 minus. This with a H plus ion. We, of course, got H plus because we have just used Cl minus. We still have a proton with us. Now with that proton, we get ZnCl2, which can again be used. And then water. So that is how we got the alkyl chloride and then water. Okay. So the interesting point here is the carbocation intermediate. We know that when there is a carbocation intermediate, we'll have rearrangements. Okay. Next. We can give the reactivity orders. Reactivity order of alcohols can be given as 3 degree, 2 degree, 1 degree, which of course is the order of stability of carbocations. And coming to the reactivity order of hydrogen halides, Hi, HBr, then HCl. A very important point is you cannot go for sodium iodide, sodium bromide, sodium chloride. These cannot be used. But why? It is because these are not acids. You have to use only the acids in this. Of course, you can carry out the reaction using a mixture of sodium halide and sulfuric acid. Okay. In this case, it will be like this. Sodium halide with sulfuric acid. We get alkyl halide, then sodium bisulfate, and of course water. Look at this. Alkyl halide. Sulfuric acid can be taken as, of course, this way, so that we can remove a water molecule. Then the remaining thing is sodium bisulfate. Okay. Even in this also, there is an interesting point. The mixtures to be used in case of this is very important. The sodium halide and the sulfuric acid mixture. Even there are some other mixtures also. We'll see them. See, in the preparation of alkyl bromides, 48% HBr is used. Then, in the preparation of alkyl iodide, sodium iodide or potassium iodide in about 95% phosphoric acid is used in the preparation of alkyl iodides. Okay. Next.